So what if I told you that dropping your hard-earned cash on that crystal clear, top-of-the-line 4K or 8K monitor might actually be doing more harm than good to your eyes? Crazy, right? I mean, we are constantly conditioned by marketing to believe that packing more pixels into a display guarantees a better, safer, and more natural image. But today, we're going to dive into some really fascinating source material that completely challenges that assumption.
Welcome to The Explainer. I'm super excited to have you here as we continue our deep dive into the documents surrounding modern digital displays. Today, we're opening up part 3 of our investigation into subpixel rendering. As always, we'll be taking a strictly impartial look at the source material, breaking down some highly debated claims about resolution and clarity. We're going straight to the data, right from the research, to uncover the physical reality operating behind the glass of your screens.
Okay, let's dive right into this. If we look over the last 30 years, we see two very distinct trend lines mapped out in the research. In blue, you've got the steady, and then frankly exponential climb of display resolution. We're talking moving from 720p to 1080p, and then just rocketing up to the 4K and 8K standards we have today. But right alongside it, in red, the sources track a sharp, simultaneous rise in reports of critical digital eye strain. The author points out that as 8K technology surged around the 2020s, retinal stress literally hit critical levels. So, the data here poses a profound question. Is this just a massive coincidence, or is there a direct physical correlation going on here?
To figure that out, here's our roadmap for today's explainer. 1. The resolution paradox. 2. The illusion of clarity. 3. The 4K and 8K trap. 4. Anatomy of an assault. And 5. Rethinking display technology. Let's get right into it.
Section 1. The resolution paradox. Claims versus reality. The sources give us this incredibly detailed table to directly contrast what they call algorithmic lies against their models of physical reality. Today, we're zooming in on 3 specific claims. First up, Claim C6, that closer emitters equal pure colors. Then, Claim C7, that subpixels improve resolution. And finally, Claim C8, that 4K and 8K screens are sharper and safer. Now, the author argues that these are really just algorithmic illusions that completely ignore microscopic light interference and the actual physical demands placed on our hardware.
Section 2. The illusion of clarity, pure colors and sharp lines. So, the industry generally claims that by making subpixel emitters smaller and packing them closer together, the screen naturally produces pure colors and razor-sharp lines. Makes sense on paper, right? Well, the physical reality presented by the source text asserts something very different. It argues that because these tiny red, green, and blue subpixels don't actually physically overlap in space, they cause microscopic light interference. And according to the research, this creates a persistent edge haze, and this is absolutely crucial. It lacks a single focal plane for our eyes to lock onto.
Take a look at this. On the left, we have a theoretical real color pixel, and over on the right, the subpixel array that's currently used in almost all of our modern devices. Just look at the color bleed and those blurred edges on the right side. According to the author, the color you're perceiving isn't actually an optical reality at all. It's an exhausting neurological illusion. Basically, your brain and your ciliary muscles, the tiny muscles that control your eye's focus, are being forced to continuously overwork to merge these spatially separated spots of light into one coherent image. That constant subconscious struggle to find a focal point, that's what the source pinpoints as a massive cause of neural load and cognitive fatigue.
Section 3. The 4K and 8K trap. Escalating hazards.
Now, what's really interesting about this slide is the mathematical shift in energy. On the left, you've got a standard 1080p pixel. It has a relatively moderate emitter area and produces a nice, broad energy spike. But on the right, we're looking at a high-resolution 4K or 8K pixel. Because the resolution is just so much higher, the physical emitters simply have to be mathematically smaller to fit on the screen. The source points out that to achieve the exact same perceived brightness for you, the user, that energy spike has to transform into an extremely thin, intensely sharp needle of light. An energy needle, literally.
Let's logically walk through what the source defines as the Subpixel Glare X-Factor equation. It's actually pretty straightforward. Step 1, you buy a display with higher screen density, like an 8K monitor. Step 2, this physically demands a much smaller emitter area, represented as a lower Y, for each subpixel. Step 3, to keep the screen looking normal and bright to the human eye, the display has to drastically overdrive the peak brightness of that tiny area, resulting in a higher subpixel glare or a higher X. Step 4, the final result is sharper, highly concentrated energy beams. The vital claim here is that shrinking the emission area doesn't actually make the screen safer, it demands a dangerous increase in peak brightness. It's a real catch-22.
Section 4. Anatomy of an assault. Biological reaction.
So the crucial point of biological failure happens right at the pupil. You see, the pupil is our natural evolutionary defense mechanism against bright light. But there's a catch. It only reacts to the spatial average of light. It dilates based on how dim the overall screen looks. Because the screen's average brightness appears perfectly normal, the pupil just stays wide open. This biological loophole allows those narrow, high-peak subpixel energy beams we just talked about to completely bypass our natural defenses and strike the retina directly with full force.
The sources use a fantastic analogy to explain this mechanism: the magnifying glass effect. Think about how a magnifying glass can focus perfectly safe ambient sunlight into a tiny, burning focal point, while subpixel rendering acts the exact same way. The comfortable average light essentially masks the fact that these invisible, highly concentrated peak energy spikes are acting like burning points, piercing directly into tiny clusters of our retinal photoreceptors. Yikes, right?
And this brilliantly illustrates what happens next. Since the pupil has failed to block the intense energy, the eye triggers its secondary defense, the orbicularis oculi. Those are the muscles that close your eyelids, activating the squint reflex. The research maps how these concentrated energy spikes cause continuous, involuntary microcontractions. Basically, you are micro-squinting all day long, without even realizing it. Over time, the source firmly asserts that this constant unnatural muscle tension is the absolute physical root cause of chronic digital eye fatigue, headaches, and visual exhaustion.
Section 5. Rethinking display technology. Hardware-level reform. Now, impartially reporting on the proposed solution, the author introduces a patented architecture called the Real Color Pixel. This technology, which holds the patent US 9310051B2, reportedly utilizes an optical lens structure to physically merge RGB light into a single, solid, pure color pixel. By eliminating the gaps in the fragmented array entirely at the hardware level, the author states it resolves the native flaws of subpixel rendering. It essentially creates an optical solid color without the need for those dangerous concentrated energy spikes we've been discussing.
The overarching struggle to bring this hardware reality to the forefront and push back against established industry marketing is powerfully summarized by this quote from the author, Yuen Chu Wang. Scientific truth exists in natural reality, not in the approval of peer review. The texts strongly advocate that we really must replace algorithmic consensus with actual, physical, glare-free hardware reality.
And that brings us to the end of today's explainer. Based on the physical models, the X-factor mathematics, and the physiological data presented in these sources, we are left with a pretty provocative question. Are you willing to look past the marketing hype of pixel density? The next time you sit in front of a stunning, ultra-high-definition 8K display, I invite you to consider the invisible energy spikes and the true physiological cost hiding right behind that illusion of clarity. Keep questioning, keep learning, and we'll catch you in the next explainer.